Thank you, Andrea, for the introduction, and thank you to the Intelligent Science in Summer School Organization Committee for inviting me to give this tutorial. It's a pleasure to have the opportunity to share this with you. So, as Andrea mentioned, we will be discussing on variational autoencoders for audiovisual speech enhancement. This is joint work with a few people here. So it's mainly Mustafa, who was doing, let's say, the dirty job. And we got lots of help from Simon, Laurent, and Radu to do this. As Andrea mentioned, I am with INRIA, which means that I am also affiliated to the University of Grenoble, and I am also part of the Multidisciplinary Institute of Artificial Intelligence, also in the region of around Grenoble. So when Andrea invited me to give this tutorial, I was a bit hesitant. Because behind some of the things that I'm going to discuss, there are lots of maths, and so don't be afraid. There are some equations, but there are not tons of slides with plenty of equations, which means that from time to time, some of the results that will appear in the slide may feel a bit magic because they come out of the blue, but this is because the format of a tutorial is maybe not the appropriate to give lots of mathematical details. But of course, all what I'm discussing here is available online. So you can take a look to the math if you're interested, and I will be available by email afterwards to discuss some of the mathematical details if they are not clear. So what are we going to do today? We are going to, now. So can you still see my slides? Well, no one is complaining, so I guess everything is fine. So we are going to discuss a little bit about what we called unsupervised audiovisual speech enhancement. Then I will present the main tools that we use for doing that, which are deep probabilistic generative models. And then I will present two instances of, let's say, VAE-based methods for audiovisual speech enhancement. So let's start with what do we mean by unsupervised audiovisual speech enhancement? So the task of speech enhancement consists on extracting the clean speech signal from a noisy mixture, or in other words, to remove the background noise. Okay, so we will be working in the short time Fourier transform domain. This is our basic representation, which means that it's the time frequency representation and can be understood as a matrix. So you have an example here. We will be working with a noisy mixture we will call X. X has as many rows as frequencies, as frequency bins has the short time, the Fourier transform, and has many columns as windows on the short time Fourier transform. Okay. And then X will be considered to be the sum of a clean speech signal that we will denote by S, and then a noise signal that we will denote by B. And the task, of course, is given the noisy mixture X, obtain a good estimate of the clean speech signal S. So, so that is speech enhancement. Now, when it comes to audiovisual speech enhancement, the idea behind this is to use vision to help enhance the speech signal. And this is possible because the movement of the lips contain some information of the speech, that can be used to improve the enhancement output. So vision does not contain all the information in speech. It's part of it, but when the audio signal is noisy, we can actually hope that the vision will provide some decent information to enhance the speech signal. And now all the questions that we'll be discussing after I have presented the main methodological blocks will be how to fuse the vision and the audio to actually have better speech enhancement. But before doing that, I would like to just add a quick disclaimer here. I named this "Be aware of multimodality." So there are two things that we are not worrying about here, is synchronization and calibration. So we basically assume that the audio and visual signals that we have are synchronized. This means that they correspond on time and that they are calibrated. So it's that I don't have to worry if the vision and the audio correspond to each other. So I have the image of the lips and I have the recording of the audio, and I work with this directly, so I don't have to worry with these two issues. In general, when you work with audiovisual data, you have to worry also about these issues and maybe more, but this is out of the scope of this talk. So in our case, we will be focusing on how to obtain the best representation for speech enhancement. Now I'd like to tell you about the difference between supervised and unsupervised speech enhancement or audiovisual speech enhancement. So when we work with in the framework of supervised speech enhancement, this is what it can be seen in figure 1, we have at the input of the method, in this case it's a network, it's going to be a network anyway. So at the input we have the video frames and we have a noisy speech. And then at the output we have, let's say, the clean speech. So basically this network, maybe an encoder decoder or maybe something else, it's actually denoising the speech with the help of the visual frames, okay? And this implicitly means that the network is learning the characteristics of the noise, the statistical distribution of the noise. Okay, so this is what we call supervised. It's supervised in the sense that the network is learned for specific types of noise that are seen at training time. In our case, we will actually be learning a generative audiovisual model for clean speech. So at training time, we will use only clean speech. And then at test time, we'll have an unsupervised noise model. This means that at test time, we will be learning the noise statistical model. And therefore, our trained generative model is not trained for specific noise type, but is trained for just to model the speech signal, the clean speech signal. And then we deal with the noise at test time. And therefore, our method is independent of the noise type. So in particular, what's going to happen is that at train time, we will train a generative model with clean speech data, and we will hope that this p theta of S, which is the probability of the signal S, resembles or gets close to the actual real probability. And then at test time, we will have the signal S combined with noise, okay, and we will observe the mixture X. So we will not observe S, we will observe the mixture X, and we will have to learn the parameters of the noise, which are these theta here, and at the same time infer the latent variable S, okay? So while at training time, S is an observed variable, at test time, S is a latent variable, and we have some extra parameters theta that have to be learned. Luckily, what we have learned at training time, which is this theta, will be frozen at test time, and we will not update the parameters of, as you will see, the variational autoencoder. So before going into how to use VAEs for speech enhancement, I would like to be sure that we are on the same page and that I would like to just introduce the basics of VAE. So in the objective of generative models is to train a complex data distribution. So a parametric probability distribution, P of theta, that approximates a complex data distribution. So you have on the left, let's say, the distribution of the training data, which is P data. And when you do learning, you actually estimate the theta that make P theta as close as possible to P data. Okay, of course, it's not going to be exactly P data, but the advantage of this is that one should be able to sample from P theta, which is not the case from P data. Okay, so basically what you want to do, given a training set, is to minimize the differences between these two distributions. And this is basically minimizing the Kullback-Leibler divergence between the two distributions. And one can easily see that this boils down to actually maximizing the log likelihood of P theta under the expectation over P data. Okay, and this is what you are for sure see tons of times. So you have this Rmax, I'm reading the box now, this Rmax over the experimental average of the log likelihood. Okay, so this is also called minimum risk problems, right? Okay, so this is the aim, is maximizing this likelihood. So in our case, we are going to be using latent variable generative models. So this means that we have an observed variable. This is going to be our speech signal S, and there's going to be a latent variable Z, which is supposed to be a concise representation of S. Concise in the sense that the dimension of Z is much smaller than the dimension of S. Okay. So this means that I will have so-called prior distribution on Z, and then I will also have a posterior distribution of S given Z. And then all the difficulties is how to obtain P theta of S, which of course can be written as the marginalization of the joint probability, but actually computing this integral is really, really tough and impossible for the models we are going to be discussing. And all the, let's say, mathematical tricks necessary to obtain P theta of S are exactly due to the fact that this integral cannot be computed in closed form. Now, once we obtain P theta of S, we can actually, once we estimate the parameters theta, we can actually draw new samples very easily, first sampling Z, and then obtaining a sample of S from the posterior distribution. Now, the problem is, or the challenge is, what are these theta and how to estimate them? As I was saying, this integral doesn't have closed form, so we will have to find ways to approximate as much as we can this P theta of S during training. So usually P of Z is, this is the prior distribution on the latent codes, is considered to be a standard multivariate Gaussians. This means that, and I am being a bit loosey with my language, so we are transferring all the modeling responsibility to the posterior distribution, okay? We are only learning the parameters of the posterior distribution. So you have one very classical example of this is when the posterior distribution is a parametric Gaussian with a linear model. And this is basically called probabilistic PCA, okay? In that case, because of the linear dependency between, of the mean of S and Z, so this AZ plus mu, thanks to that, we can actually compute the integral, and the parameter estimation is straightforward. The problem is that this is a very simple model, and it is not expressive enough for many tasks. So we go and look for more complex models, which are going to be basically a non-linear dependency of Z. Okay, so this means that this posterior distribution depends in a nonlinear form of Z, and these nonlinear functions are usually implemented as deep networks. It could be with something completely different. The problem is that because these are nonlinear, then the parameter estimation is challenging because we cannot compute the integral in closed form. But the huge advantage is that the nonlinearity makes the generative model much more expressive, and we can actually model complex data with that. So it is very interesting for this reason. And okay, just to more or less conclude towards variational autoencoders, this nonlinear Gaussian dependency, as it is presented here, with some additional tricks that I will discuss later, is the so-called variational autoencoder. So when we try to, when we attempt to go for estimating the parameters, I'm pretty sure that you have heard about expectation maximization algorithms. So I will briefly here discuss the relationship between these EM algorithms, also because we will use them later, and with variational autoencoders. So everything starts with this log of the marginal on S. And of course, I can take the expectation over any distribution Q phi of Z. Since log p theta of S does not depend on Z, this expectation does nothing. Okay, so I can do this for any distribution Q phi of Z, Q psi of Z, sorry. And of course, I can multiply and divide by the same amount, which is the true posterior times Q psi. And by manipulating this, you can trust me on this, you don't have to verify, we can get to these two terms, okay? And these two terms are the basis of the EM algorithm. The first term is a so-called E step that I have to minimize. And I minimize this when I make Q psi equals to P theta old, let's say, for a given initialization of the parameters. So this is when I say that I use the true posterior, okay? And then I have the M step, which is basically optimizing the first term with respect to the parameters. So this is the so-called EM algorithm, and it has two problems for variational autoencoders, is that the E step, so basically P theta of the posterior of Z given S does not have a closed form solution because of the nonlinearity. So then I cannot say that Q phi is just, something simple. This equality is, it's very difficult to obtain an analytic form for this. It's actually not possible. And the same problem happens when I am on the M step, okay? So therefore means that this, when we have no linearities, this is very hard to use. And we are actually going to do something that is a little bit different. We are going to ignore the KL divergence term, which is strictly positive, and then say that this is greater or equal than the first term that I decomposed in two, okay? And these two terms are what are used to train a variational autoencoder. The first term is a so-called reconstruction term, and the second term is a so-called regularization term, okay? Exactly. So, and then this quantity here at the last line is the so-called evidence lower bound. And this is what is maximized when we train a variational autoencoder, okay? So now that I have presented this first set of equations, I think I am ready to discuss a bit more in detail what a VAE is. So I recall the generative models. We have a standard multivariate Gaussian distribution for the prior on Z, and I have a posterior distribution that depends in a nonlinear way on Z. Then what VAE does is approximate the posterior distribution with a parametric Gaussian distribution, is this Q psi of Z given S, that depends in a nonlinear way of S. But here, just be careful, they are not the same parameters. The generative model is using theta, and the posterior distribution approximation is using psi. So this means that the network that is on the generative model that you can see here on the right, that is generating S from Z, can have a certain structure and certain parameters. And the network that is used for inference, it's computing the posterior distribution of Z given S, it can be a completely different network with a completely different set of parameters. Okay, and now the question is how to train this. So you have to put all this on the evidence lower bound that I showed before. And then as we will see, and then you obtain this. Okay, so you have the expectation over the approximate posterior of the log likelihood of the posterior of the generative model, and then the regularization term. And because the expectation cannot be computed in closed form, what you do, you sample. You sample from the posterior distribution, you obtain this ZPC, and then you replace this in the term inside. The problem with that is that we want to train this with stochastic gradient descent. And okay, all the operations in the evidence lower bound that you can see above here are differentiable except for the sampling. Okay, so if ZPC is sampled directly from Qphi, we cannot compute, we don't know how to compute the gradient with respect to phi of the sample. Okay, so we use something different. We use the so-called reparameterization trick. It's a very simple idea. Basically, now I'm sampling from standard multivariate Gaussian, and then I'm multiplying the covariance matrix, or actually the square root of the covariance matrix. And I am, there's a small mistake here. And then I am adding the min. And now we decouple the sampling operation from the parameters, which are computed by the network. And now we can, of course, compute the derivative of ZPC with respect to the parameters psi. So this, that here is done with Gaussian distributions, can be done for any distribution in which you can decouple the sampling, which is epsilon here, and the parameters that you are training for the inference. Okay, now that we have seen the basics of VAEs, I can start describing how did we use VAEs for audiovisual speech enhancement. So let us start with a very simple case. We forget about the vision right now. We are going to assume that S is my clean speech. Then I have Z, the latent code, and then I can learn an audio-only VAE. Okay, this is a direct application of what we have seen just before. Okay, I have audio input here on the left of the input of the encoder. This forwards the encoder, estimates the parameter, then I sample from the standard normal distribution. I obtain a Z. I go forward with that. I obtain an S. I compute the loss, and then I backpropagate the error. Okay, standard variational autoencoder that allows me to train an audio-only generative model that we can see here on the left. Now, we can also think about a video-only VAE. Okay, a video-only VAE would mean that I will take as input a visual frame. I will pass it through a network. You can see the details of that. I am simplifying this a little bit. Actually, this is gone through a convolutional network that extracts some features, and these features are given to the encoder. The encoder, in the same way, computes samples from the posterior, and then does the generation part, and then backpropagates. The point here is that we are our posterior is based only on visual information. So we call this video-only VAE, even if we are using audio for training, because of course we are comparing SN to the clean speech signal. So these are for audio-only and video-only VAE. So now, we started thinking how to put this together. Okay? And a very simple way to do that is concatenating audio and vision. And when we were checking the literature, we saw that the architecture that was most convenient for that was the so-called conditional VAE. And you can see here that both the prior on the latent variable and the posterior of the generated variable given the latent variable, both of them are conditioned by Vn. So Vn is going to denote here the visual features that we have extracted with the convolutional net. Okay. So, and then of course, the inference network, which is the posterior of Zn given Sn, is also going to be conditioned by the vision. Okay. Otherwise, it doesn't make much sense. And this is actually what's going to happen. So I am saying that my speech is conditioned also by vision, this Vn, and then that my posterior distribution of Zn given Sn is also conditioned by vision. And I have also said before that the prior distribution of the latent variables is also conditioned by vision. Okay, so I have vision here helping at 3 different places. On the prior of the code, this is on the bottom of the slide. On the posterior of the generative model, this is on the right-hand side, top right of the slide, and on the posterior of the inference model, which is on the top left of the slide. Okay. And here, as this is an important point for later, you see that vision is always there. Okay, I am always using vision in these 3 places. Okay. So when I want to train this, I have, of course, the audio, which is Sn, but now I also have the video, Vn, for all the training set. And then I use something that is not exactly the evidence lower bound as it should be, because I have this alpha here and 1 minus alpha. And we use that to force the network to learn from the video. Okay, and let's make a pause here to explain what I mean by this. I recall you that I told you at the beginning that we were training with clean speech. Okay, so if we train a generative model with clean speech, there is no reason whatsoever for which the network would actually use visual data to learn. Okay, so if we train as it is directly, then the network is just ignoring the visual stream, because to reconstruct clean speech from clean speech, I don't need anything else. So this factor alpha here, it's actually giving some importance to reconstructing only from video. And this is allowing, so it's actually reconstructing from the prior. Okay, the prior that depends only on the video. And this is actually being useful to prepare the generative model to be initialized with visual information later on when there's going to be noise. Okay, so now we can, once the VAE is trained, I told you there are 2 phases, train and test, and this test is what we call the speech enhancement. So at train, we train the parameters of the VAE, we fix them, and now we are worried about learning the parameters of the noise for an unknown noise type and inferring the clean speech signal S from the noisy mixture X. So our probabilistic model here is the following. I am going to say that X is the sum of S plus noise B. This is deterministic addition. And then the noise B is going to have a certain amount of energy that is given by a non-negative matrix factorization model. Let us just not go into the details here. It's just the product of 2 matrices. And the clean speech model, of course, is what we have discussed before, is this conditional audiovisual VAE. Okay, so now when I am at speech enhancement time, I have to do two things. First, I have to learn the parameters of the noise, eta. And then once I am done learning that, I have to provide an estimate of the clean speech signal. So we will derive an expectation maximization algorithm in which we have the parameters are eta, the parameters of the noise. The observed variable are the noisy mixture X and the video V. And then the latent variables are Z, because actually I can integrate S out during the learning of the parameters. And then I will need the formula to actually find the best estimate for S. So this is one moment in which I skip some details, but I provide some others. So actually, due to the nonlinearity in the variational autoencoder, the EM algorithm is not a closed form EM algorithm. We need to use sampling, okay? I use sampling to approximate the expectation that you can see here in this big Q function. And then I can maximize over the parameters of the noise using some multiplicative update rules. Okay, so this part, the M step here, has closed form. The one that does not have closed form is the E step. And then once I have done that, at the end of this MCEM algorithm, I can use the formula you have here to estimate speech, the clean speech. So for those who have never seen a Wiener filter, this may look very strange. For those who have seen a Wiener filter, this may look very familiar. So the Wiener filtering at the end is very intuitive. It's telling me that I have a certain amount of energy associated to the speech signal. This is this sigma SF. And then I have some energy associated to the noise, which is this WH, and then I extract the FM coordinate. This is not really important. So basically, if my clean speech, so the estimated energy of the clean speech is higher than the noise, I will basically use XFN here on the right as the clean speech signal. And if it's much lower than the noise, I'll basically set this SFN to 0. Okay, so this is what the Wiener filter is doing. It's a very simple rule that is obtained from the probabilistic model, telling me that when I believe that the speech energy is higher than the noise, I take the observation I have. And when I believe the speech signal has much less energy than the noise, I'd rather set this to 0, because there will be mostly noise in this time frequency part. Okay. So let us present and discuss some experiments. You can see here that we have used the NTCV-TIMI dataset. This has some particular reasons why do we like that. As audio and video are synchronized, they are recorded in control conditions, so we consider these speech, clean speech signals. And then what we do is consider different noise levels and also different noise types. Okay. Okay, so here you have some details on the architectures, but I'll skip this for the sake of time. Once again, you have all these on the available manuscripts available online. And so we evaluated this until 3 different performance measures. The first one is objective, while the 2 other ones are subjective, and all of them are the higher the better. And what we should, so we should take a look here to the turquoise curve, which is the proposed method. You can see here that when in very low SNR cases, meaning that the speech, so that the noise is very high, of course, the audio-only speech, the audio-only enhancement is very bad. This is the blue curve. The video-only enhancement is very good. that's the green. And when we are in the other side of the spectrum, meaning when the noise is really low, okay, audio is doing very well by itself, and then vision is actually not helping much. So here, what we are measuring is the improvement with respect to the input. So it's a bit tricky to understand this. So it's basically how much is it helping in each of the situations. Okay, so vision is basically not helping when I have very few noise, which is normal. But what is important here is that if you take a look to the turquoise curve, is good in both cases. So it's close to vision when noise is very high, and it's close to audio when noise is very low. And this means that we actually succeeded in fusing audio and vision for speech enhancement. Okay, and this is repeated roughly for the three measures, maybe not for STOI, it's a bit more difficult to interpret. So, as I said before, one limitation of the method that I have presented is that we are using vision systematically all the time. And then one may wonder what happens if in some cases vision is actually not helping. So we devised a second strategy, which is actually selecting if I should pick audio only, vision only, or actually any combination of these two with different weights. Okay, so we call this a mixture of inference networks, and you can see the structure here. So I have a vision prior, an audio prior, and then I am picking up from these two guys a mixture, like a probabilistic mixture, to actually sample from that. Okay. So the model is a little bit more complex. Actually, the generative model of the source S is the same. Because I have one single decoder, as in the previous case. The difference is that my prior Zn can be sampled from two different normals, depending whether a sample is more like audio or more video. Please notice that this is not annotated. So actually we don't know if alpha is 1 or 0, this alpha n here. And this is why alpha has a probabilistic model as well, okay, which is a Bernoulli distribution. So this is like mixture of two Gaussians, but like after mixing the two Gaussians for the prior, then I have a nonlinear model, okay? So I have a mixture of Gaussians for the prior and then a nonlinear model for Sn given Zn. And now the question is, how do I have to describe the posterior distribution, which is the encoder network, to actually work with that, okay? So if I write the posterior distribution of Zn and alpha n, I recall, and I insist on that, alpha n is a latent variable as well. This is the exact posterior distribution. So I have the code posterior given alpha n, and then the mixing posterior. And actually, neither of them are tractable. So I have to resort to some sort of approximation. And what we will do is say, okay, my posterior of the latent codes, if alpha n is equals to 1, so I come from audio, then I will approximate it with an audio encoder. And then if I come from video, I will approximate it from some video encoder. Okay, so I have two encoder networks. And then I need an extra approximation to approximate the posterior of alpha n, okay? And then this is another point in which I skip the details because it took us a lot of energy to do that. I wanted to show the, I will show that later. Okay, so when I want to train this, now I have an extra problem because, as I said, I have two latent variables, the latent code Z, but also the mixing variables alpha. And then I have a bunch of parameters to be estimated. We keep on using a lower bound on the data log likelihood. It is a bit different than standard VAEs, but let's not go into the details now. We obtain a variational EM when doing that. The E step is actually estimating the posterior of this mixing variable alpha n. And you can see here that the posterior is also Bernoulli distribution. And PM, which is the parameter of this posterior distribution, is actually the prior parameter P times an extra term, okay? And this extra term, which is Gn, so Gn is the standard cost of VAE representing the nth vector with audio or with video. And okay, G is the sigmoid function. So basically, how do you have to interpret this? Because this is the most important thing. If Gn of alpha n equals 1, okay, the first term inside G is much larger than the second term inside G, it means that it is easier for the audio VAE to represent the nth vector than it is for the video VAE. Okay, so this will push Pn to be close to 1. So this will push the posterior of alpha to say, hey, we have to infer this from the audio posterior, not from the video posterior. And it's the other way around, of course, if Gn of alpha n equals 0, so the second term inside G is larger than the first one. And then the M step is actually a bit painful to describe, and at the end we are doing standard, something close to standard stochastic gradient descent, so it's not worth going into the details. It's just that for those who are familiar with Gaussian mixture models or with any mixture models, when I have to update pi, and I end up doing basically the average of pi n, which is again one standard formula that we can see when working with mixture models. Okay, so this is just to say that even the maths get a bit complex, everything makes a lot of sense, and we actually end up obtaining something that is very reasonable in terms of interpretation. And we will see how it works in the experimental section. So this is for training the mixture of inference networks. I will try to go fast because I don't have any minutes left. When we are doing speech enhancement, we face a similar problem than before, but a little bit more complex. So now we have to learn the parameters of the noise. Okay, the encoders and the decoder are frozen, but we still have now 3 kinds of latent variables. So we have the clean speech, which is a latent variable now. We are at speech enhancement time. The codes, which are always latent, and the mixture variable alpha n, which is always latent. Okay, and if we run this, now I put even less details because it requires really a lot of derivations to obtain this. We obtain a variational EM this time, in which we are able to obtain to update the 3 posterior distributions of S, Z, and alpha, and to update the parameters eta. And then once again, when we are running the speech enhancement phase, we obtain an average binaural filtering as in the previous case. And when here gamma, this gamma Fn represents the posterior energy of the speech at time frequency point Fn, just that we put gamma because the expression of this is a bit complex, but it actually plays a similar role. So once again, we obtain a binaural filtering, which for people that come from speech enhancement is actually quite reassuring. So in here we tried 2 kinds of architectures. The first one is using vision on the generative model of S, and the second one is not. Okay, and we train both and then we compare both. So if we do that, so of course we obtain the same thing for the audio VAE, the visual VAE, and the audiovisual VAE, meaning the conditional autoencoder, variational autoencoder that we saw in the first half. And then we have these 2 extra curves here, and they're the ones that we would like to discuss. So one can see here that the best strategy overall is the green curve. Okay. Sometimes the conditional visual VAE is superior to this, but many times the second version of the mixture of inference networks is superior, especially when at training time we add some noise to the audio encoder. Okay, so this is the second row of results. And then in that case, we obtain really superior results with the second version of the mixture of inference network. So I think I'd rather stop here. So I wanted to extract some quick conclusions. So first of all, we have actually VAEs demonstrate that that are really nice to model speech and that are very useful to then combine these probabilistic speech models with a probabilistic noise model and run an EM algorithm for the speech enhancement phase. So, but it has some things that we can improve. First is that sometimes this requires sampling. This requires algorithms like a variational expectation maximization that have slow convergence. So there are strategies to mitigate these problems, like reusing the trained encoders at inference time. And this can reduce the complexity, but it is unclear if it will have the same performance. So we are investigating that. We would also like to extend this mixture of variational autoencoders, or of actually mixture of inference networks, to more than 2 encoders, maybe also to include some other sources of information. And finally, it would be really interesting to actually have some temporal modeling of the latent variables, because if they have to represent the underlying speech signal, of course, this speech signal has some temporal consistency. So on this note, we have very recently published, shared online a review on what we call dynamic variational autoencoders. So this is a new model class that actually covers many works in the literature. And we have specifically reviewed 7 of these works that you may recognize. Here are the names. We re-implemented all these, and the code will be available soon. And there is a huge long preprint in archive that has more than 100 pages. So if you are curious about it, we will be very happy to have your feedback. Just be aware that it may be a bit long to read. Okay, so I'd like to thank you for your attention, and I'd like to take questions if there are any.